Alright, ladies and gentlemen, we are going to be taking a look at one of the hardest concepts in this unit. This is Unit 9, Electric Fields, taking a close look at our learning targets. This video is going to cover the first two right on over here. I can relate electrostatic ideas to gravitational ideas. Like we saw on Friday, there are great parallels. We're going to make a nice little t-table to look at those parallels. And number two, I can understand how electric fields work and how to use it in calculations. We will actually develop the equation today, and then we will be using that on Monday with our worksheet. So let's dive right in. First idea is parallels. So if we actually drew a nice little t-table and organized our ideas between the parallels, this is gravity on over here, and this is our electrostatics. First thing that we want to connect between the two is understanding that they both are long-range forces. They both happen across a long range. So because of this, we actually need to go into the next idea of understanding that we need an idea between these two that allows us to actually act across a long range, and that is going to be a field. That is why we use fields. It describes that interaction between the two. So because they both share these properties, that means they both need to really follow the idea of a field. With that said, gravity affects the idea of mass, or m. So you're going to see in a lot of our equations, you will see the letter m appear. And instead, in electrostatics, we deal with charge, which is going to be represented by Q. So you'll notice the equations are almost identical to each other. The only difference is instead of m, you're going to see the letter Q in place of it. Other ideas, we have Fg, well, that is our long-range force, and over here we are going to have Fel. Again, the equations are going to be really similar, and we can make the parallel there. Of course, you will see Eg, which is the energy stored gravitationally, and on over here we are going to have El, that is the energy stored elastically. Again, some great parallels between the two. They will share some differences, however, especially in that case. And last but not least, we have gravitational potential, usually represented by a V, G, that is gravitational potential. And then on over here, we are going to have VE, which is electric potential. We will discuss that in the second video. So my main idea is if you can understand everything that's happening on this left-hand side on over here, if you can run the parallel, you should be able to run the equations and the calculations on over here. So I think we all feel really comfortable with gravity. I know I always relate back to gravity when thinking about electrostatics. So going back to our targets, number one, boom, done. I can relate electrostatic ideas to gravitational ideas. Now, electric fields, how do they work and how to use it in calculations? Well, yesterday when we looked at it in class, we looked at Earth. And we knew that Earth has this idea of a gravitational field that is constant going downwards. So if I drew this in, this is the idea of, we used 10 newtons per kilogram. It is really 9.8 newtons per kilogram. That is representing each one of these arrows drawn in here. So if I looked at this arrow right here, it is just again a representation of what the force would be on a mass that would be in that object. This stands for what we call G, which is the gravitational field. So if that is our gravitational field, notice that the gravitational field G is equal to a force divided by a mass. So notice it is Fg divided by m. It is whatever the gravitational force per mass is, and that is equal to the gravitational field G. On Earth, you will notice that that is going to be the 10 newtons per kilogram. That's one we're used to using, but depending on the planet that you're on, that may change. That could be 20, 30, 40 as you get into different planets in different situations. You'll also note, if you take a look at the Earth from a larger scale, that is near the surface of the Earth, so G is again about 10 there. But as you get further away, remember that will decrease, and that value will get smaller and smaller and smaller as you get further and further away. So that is just representing that arrow in our drawing there. So the parallel to that, again, we're looking at Earth creating a constant gravitational field. When we actually make the parallel, to create a constant electric field, we saw in that example, if you place two plates that are charged a certain distance apart, they will create an electric field. Remember, the positive charges will create a downward electrical field going away from it, because remember, electrical fields will tell us which way a positive charge will go. So that is going to be like this. And then, of course, as we get further down the road on over here, if you're by a negative, again, arrows will go into the negative, showing again the force that a positive charge would feel if it's near the negative, which it would be attracted. And because these plates are loaded with charge, we will actually create a constant electric field there. So this is the electric field. Will be represented by just a straight E. You might think that's energy. Please do not. That is, again, electric field. And as we learned, the units for this is going to be newtons per coulomb. Again, the way that I think about this is very similar to when we go on over with gravitation. A newtons per kilogram tells us how many newtons an object would feel if it were 1 kilogram. So if we go on over to this electric field, this is telling us how many newtons per coulomb. So again, if you have 1 coulomb of charge, that charge will feel that many newtons there. And so the equation that comes out of this is going to be F. Again, that is the force, the electrostatic force. But instead of dividing it by mass, we are dividing it by Q, or the amount of charge. So this is a very easy calculation again, and you guys were running this calculation when you were taking the electric field and multiplying it by Q. So going back on over here, kind of taking a zoom out and looking at this parallel, you will notice F divided by m is equal to the gravitational force, and F divided by Q, which is equal to the electric field. Notice how similar these two equations are. The only difference is we've replaced the m with the q. So going back to our learning targets on over here, this video wraps up the idea, the first two on our list here. I can relate electrostatic ideas to gravitational ideas, and I can understand how electric fields work and how to use it in calculations. And so we used these calculations before. Again, electric field, force divided by Q. Next video we'll talk about the other two ideas. Please make sure you look at that. And we'll talk about it more on Monday.